Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 122, Digital 2. Today we're going to finish up our shift registers with some applications for shift registers. My first and favorite application, it should probably be yours too, lazy math. So remember way back when we were doing binary multiplication, if you wanted to multiply 4 times 2, you'd have to add 4 to itself twice and vice versa, constantly doing those successive additions. Well, what you can do is if you want to multiply by 2, 4 times 2, why not just shift it? You know, because this is the 4 position, that's the 8 position. What you've done is basically just shifted it from the 4 to the 8. Okay? This also works for division by 2. Say, for example, we want to divide 4 by 2. Well, shift it the other way. There you go. So we've gone from the 4 weight position to the 2 weight position, because we know 4 divided by 2 is 2. 4 times 2 is 8. For example, 5. Multiply that by 2. Just shift it, and you get 10. Divide it by 2. Shift it the other way. We're going into the decimal zone. Remember, that's 2, that's 1, and that's a half. 2.5. Pretty cool, huh? Second application for shift registers is time delay. Basically, we've got something coming into a system and just put it into a serial in shift register, serial out shift register, give it a clock signal, and it's going to be delayed when it comes out the end. So here's a 4-bit shift register where here's our data coming in, and here's Q3, our data coming out, and right here is basically our positive edges. Basically what's going to happen is that positive edge, I'll make sure this is going to reach it though. You know, positive edge 1, that data shifted in to the Q0 position. Next positive edge, it's shifted into the Q1 position. Next positive edge, shifted into the Q2 position. And finally, the output, Q3 right there, at the next positive edge, is shifted into that position. Okay, so let's say this was a 1 kilohertz clock signal. So therefore the period is 1 over 1,000 or 1 millisecond. So that's a 1 millisecond delay, 2 milliseconds, 3 milliseconds, 4 milliseconds. So basically after 4 milliseconds, it's available on the output. If you want it faster, speed up the clock. Just go like 5 kilohertz. Or you could access it from an earlier stage. For example, Q2, Q1, Q0. You'd have to use something like a 74164, which was, remember, a serial in parallel shift register where the previous stages are accessible, and it's got that shift load command. So basically, as long as it's shifting, this guy's available. So Q1, let's say you want to grab Q1 right there. After 2 milliseconds, that guy's going to be available. You want it slower, add more stages. You know, have a Q0 to Q7, use an 8-bit shift register, or slow down your clock. The next application for shift registers is serial to parallel data converter, and vice versa, parallel to serial data converter. And one of the more common applications of this is the universal asynchronous receiver transmitter that has a parallel in, serial out, and a serial in, parallel out. Depending on what mode it's in, it can go either way. So universal asynchronous receiver transmitter, it's interfacing with a parallel bus and a serial out. So here's parallel in, serial out when it's in this mode. Now something's talking to it in serial, and we're sending this out in parallel when we're in that mode. Okay. Now some of you guys might be thinking, wait a second, serial to parallel, parallel to serial. Isn't this just like demultiplexing and multiplexing? And the answer is no, not exactly. It accomplishes the same purpose. So remember, it just does it in a different manner. Remember, multiplexers. Here's 4 systems going to single line, 4 systems there. 2 data selects there because there's 4 positions. So what's happening for a multiplexer, remember, is 0 is talking to 0. It's a direct connection. What are the other 3 guys doing? Nothing. Now it switches over. 1 is talking to 1. Direct connection between those guys. What are the other 3 guys doing? Nothing. They're not getting anything. So what serial to parallel and parallel to serial conversion does, it's kind of like multiplexing and demultiplexing in the fact that you're taking a parallel and going to a serial, or taking a serial and going to a parallel. But it's just basically, whereas multiplexing and demultiplexing was a single mailman delivering to a single address a part of the data selects, what that mailman is now doing is letting all the letters stock up in a shift register. Basically, let's do serial in. And here's all the letters that are coming in. And he knows that in the example of our four systems there, Q0, Q1, Q2, Q3, he's letting all, whatever the letters are, stock up there, the bits for Q0, Q1, Q2, Q3, and then delivering them simultaneously. Parallel out. Okay, so whereas a multiplexing and demultiplexing is basically a direct connection according to the data select positions, all a serial to parallel conversion in this particular example we talked about, it's basically letting the shift register fill up, in this particular case, with 4 bits, and then those 4 bits are available at the same time for all 4 systems right here, and they can just grab them. Okay, so one of the examples in your book is basically a serial to parallel converter, and how it does this here. Let's go ahead and I'll draw it. And so we've got a serial in to parallel out converter here, and basically what's going to happen here is when there's no data being sent on a line, we're just going to have a continuous high signal. And then when we want to send data, what we're going to do is we're going to send it in a very specific formula. And basically when we want data sent, there's going to be a high to low transition and there's going to be a start bit, and that start bit is always 0. Well, obviously high to low, it's going to be a 0. Then the data can take whatever form it wants to, from 7, 6, 5, 4, 3, 2, 1, and 0, i.e. 8 bits. And we know that it's 8 bits. That's the key to this thing here, is you know that you're going to expecting an 8-bit package. If you were expecting a 6-bit package or a 7-bit package, it would be totally different. But we know, this is one of those things. You're in the States. Normally, you would expect to be speaking English. If you're in Rome, you would normally be expecting to speak Italian. So it's the language already. And this language happens to be always high when no data is sent, a start bit of 0, 8 bits of whatever. Then you've got 2 guaranteed stop bits, 1 and 1. And again, if you were going to send more data, you'd go back to 0. But you'd go back to 0. But if you aren't sending data, it would just be 1 waiting for that next transition. So these are the packages here that we're going to see. We're always going to see that high to low transition after a long period of 1s, a 0 start bit, our 8 bits we want to, and our 2 stop bits. So how many bits is that? That's 11 bits. Which ones are we really concerned with? This guy. Oops. So starts and stop bits. That's like your and that's your period before you actually say something that you want to. Okay, how does the circuit work? I'm just talking about the data, but we want to worry about the circuit. So what we want to do, here's our data coming in. That's our data stream coming in. Obviously going to tie it to D, but we want to recognize this thing right here, the high to low transition. And how we do that is this little JK flip-flop right here. So it recognizes, that's D, it recognizes that first low transition. So what happens there, it's on 5 and 0, so it sets that thing, and that goes to the enable of, what is that symbol right there for our ANSI IEEE symbols? Well, 2 pulses there, that's a clock, basically a astable multivibrator. What it's going to do is just basically enables this clock, which goes to our data input register. So this thing starts clocking along at the exact same frequency as this guy right there. Also, that clock signal is sent to our counter, and it happens to be modulus 8 because we're expecting 8 bits. And finally, we have to have some means of clearing this guy eventually. And we'll get to how you do that with this AND gate right here and this one shot right here. Okay, so now clock is enabled. It starts clocking along. And again, this is a serial in, parallel out shift register. So basically, all that data is being fed in there. It's feeding in 7. Well, here, let's do it this way. Feeds in 7. Then 7 moves over to make room for 6. 6 and 7 move over to make room for 5, so on and so forth. So you get 0, 1, 2, 3, 4, 5, 6, and 7. And notice this whole time here that this counter has been counting. We're at state 0, we're at state 1, we're at state 2, and now finally we get to state 7. Terminal count goes high. Terminal count high is fed to that AND gate right there. And what's happening is and it's the same clock right there, you're enabling this thing a chance to clear. So basically it's this is again ANSI IEEE. What's that symbol? I know it kind of looks like an ohm. Let's redraw that. That symbol, it kind of looks like the clock, but there's only one of them, so that's a one shot. And we're going to take that from the low to clear that guy, i.e. reset it and wait for the other one, and clear our counter, bringing us back to state 0. But before we do that, that signal is also going to this guy's clock, because the only thing that this thing's constantly loading, you know, the output shift register, it's constantly loading. The only thing it's missing is a clock signal. As soon as that clock signal happens, everything that was in there, all 8 of those guys, are put into the parallel in, parallel out shift register, and they are available for your viewing pleasure. And then it data is high, 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 all of a sudden bang, it goes down again. The whole process starts over again, where you're feeding into this input register and then counting up. Once it hits 8, it goes ahead, clears everything. Before it clears everything, it loads it into the output available for your viewing pleasure. Rewind, restart, rewind, restart. Okay, let's go on to, oh, there's a keyboard encoder application in your book too. Just do a quick overview of that. And how this is done here is basically a scans the keyboard, constantly looking for someone pressing a key. And how it does it uses a ring counter that's been preloaded with a 0. And let's just put the 0, well, let's put the 0 at 0. And every clock pulse, what's happening is that thing is shifting. And then if remember, it's a ring, it's going back to the D input there. So basically, clock pulse goes by, it constantly scans for a 0 on, constantly the 0 moves from Q0 to Q1 to Q2 to Q3, so on and so forth. And that ordinarily would not be very important, but what you're doing is you're taking all those inputs, all 8 inputs, Q0 to Q7, 8 inputs, and putting them into the active low inputs. In the example of the book is a 74147. And 74147, that's a, normally it's a decimal to BCD, but in this particular case, they're just using the 1 through 8 inputs of it, and they're not using input 9. And they're only using the 3 outputs, 1, 2, and 4, and they're just not using 8. You could use the 74148 for this if you wanted to, too. And this is what's called the row encoder. And that's constantly, so if you think about it, the row is constantly getting a 0 on here. So it's either going to get a clock pulse 1, Q0's got it. And this guy is going to say, I got something. Next clock pulse comes along. This guy's got it. He's going to say, I got something. And so on and so forth. So it's this constant, what's going on here? Does that really, is there a key really pressed or not? And you really don't know just using the row encoder. So how you do that is the column encoder. The column encoder here will detect when there is a key pressed by use of this massive negative OR here. Okay, and let's go into the row column array thing that we're talking about here. Basically, with 8 rows and 8 columns, you can have 64 positions. Okay, and what's happening is the column is always hooked up to +5. Okay, and in between, there's no overlap there. A row and a column, the intersecting row and a column. You've got an arrangement that looks like this. So there's no intersection here. But when this guy, when your fat finger presses down on a key, pushes that there. Basically, that's a normally open switch that you've just closed. Okay? So what's happening is now that 0 that was on this guy going constantly ringing around here is suddenly connected to a row and a column now. Whereas previously these columns were just getting +5s there, now all of a sudden row and a column, a single row and a single column, are getting a 0. Okay? And now, because of this little OR gate here, we recognize, and those are bubbles there, it's recognizing anytime there's a 0 on a column, it's going to say, whoa, hey, we got something. So now, what happens there is, let's pause, let's hang out for a second via use of this one shot here. And what the one shot does, all it does is generates a pulse, and it inhibits that clock. Okay, so basically it's saying 1 the whole time, and because 1 ANDed with a moving clock signal, it's always going to be 1. So, okay, stop. We got something. Let's read what it is. Basically, all those guys, those 3 particular positions are going into, in this particular case, it's a 6-bit shift register, and they're using a 74174 for that. You could also use an 8-bit shift register and just use the first 6 positions if you wanted to. But now we've got to go ahead and somehow enable that guy with a little clock pulse using another one shot right here. So basically, row is constantly getting 0, but like I said earlier, your fat finger presses this thing down. Finally, column's got a 1, the column's got a 0. This thing says, hey, we got something, inhibits the clock, enables the clock on the shift register. Excuse me, in this particular case, it's going to be a parallel in register. It comes in, and there it is. And that position 0, 0, 1, 0, 1, 0. That's position row 1, column 2. What is row 1, column 2? Well, it happens to be the X key, and it places an X on your screen. Pretty cool, huh? And how does the whole shift register fit into this thing? Well, fits into it because we made a keyboard scanning thing there with a little ring counter, and it stored the row and the column, and ultimately it's using some memory. Where is row 1, column 2? It happens to be X. And finally, let us go over, there's a section on troubleshooting. And troubleshooting is one of those things where the shift register, there's no limit of errors that could be generated. Oftentimes, there is only one way to do it right, limitless causes of errors. One of the things to keep in mind, let's say you are trying to parallel load something. You're trying to parallel load 0, 1, 0, 1. 1, 0, 1, 0. And you're constantly getting out 1, 1, 1, 0, and you're like, okay, let's put in 1, 1, 0, 0, 0, and you get out 1, 1, 0, 0. You're like, let's just put in all 4 zeros, and you get out 0, 1, 0, 0. What's going on there? For some reason, you've got a short to VCC on that bit position right there. You're constantly getting, regardless of what you put in there, you're constantly loading that data, loading a 1. Another thing to keep in mind is, remember, your loads, your active low loads, is it constantly high? If you're not loading anything at all, you would be in a +5 situation. or maybe you're constantly loading something. You've got a short to ground. So keep in mind about that. Finally, the book ends with a system application activity regarding a security system. So let's go ahead and go over that. Okay, here's our security system here. And the key to this whole thing is this magnitude comparator right here and its connection to this shift register at the very end. That's the output shift register. It's basically this shift load command here. Anytime there's, and that's, by the way, that's the equal input there. Anytime there's an equal, there's a 1 there, and this thing shifts 1 to the right. Okay, so we have a 4-bit code, and what we're going to do is we're going to say it needs to, so we have 4 bits, 4 digits code, and our secret code, don't tell anyone, is 1, 2, 3, 4. Now some of you guys are probably at home, that's a combination of my luggage. So go home and change your combination of your luggage, because that's our secret code. And that is stored somewhere in memory. And it's being loaded into there bit by bit, or excuse me, digit by digit. So we put in a 1 into shift register B, and here's our keypad, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Number key, pound key. And we're initiating the what do you call it? Okay, we're stepping up to our keypad, and we say number. Okay, we're starting up. So we press 1. And through use of this OR gate here, it's basically saying, wake up. There's somebody at this thing that's trying to get our precious. So that is going positive edge transition. It's telling that one shot, okay, let's go ahead. And it's, in this particular example, it's using a negative edge. It's being fed to that one. And from there, that was our load command. So load the first digit. This clock right there, it's getting that low, then it comes back up. So that's its transition. It's going to say, take whatever that person entered, the decimal to BCD encoder there. So there's 0 through 9 there, active lows, and it's going to generate, in this particular case, 0, 0, 0, 1. And it's going to load 0, 0, 1 into shift register A, and because we have a preset code that happens to have 1 on it, it's being fed both of those guys into the comparator. Are they equal? As we just said, they're taking the equal output there, saying 1. Yes, they're equal. But this one shot here has produced again, a low to high transition. That's going to this clock. So basically, if they're equal, you've told this output shift register to shift 1 right. And so there's 3 leading zeros. Oh, excuse me, it's 4 leading zeros. And a 1 right there. So it says shift 1 right. You got the first number right. So now goes on and loads a 2. And you just so happen to press 2. And again, it says wake up. Enables our 2 shift registers here through that one shot. It's basically saying load 2 in. You got 2 there. Comparing them, again, 1. This one shot has produced a clock signal right here. And as that clock signal goes from low to high, we've got a 1 on our shift command, and it shifts 1 over. We're almost there. So repeat, you get to 3. We got that, and here's our output. We're waiting for that. We just pressed that, but now you press 5. And what's loaded in here? 0, whoops. And you just press 0, 1, 0, 1. Is it equal? No, it's not. And we've generated that clock pulse there. What's going to happen is load. It reloads 4 zeros with a 1 in this position. So you have to start back over at the beginning and do that over again. Whereas had you pressed a 4, that would have been a 1. And finally, that output position would have shifted over to 1, and it would enable some door lock or something like that. So the key was not that you just had the right combination, but you had to do the right combination in order, because it's successfully loading those 1, 2, 3, 4. If you press 4, 3, 2, 1, it wouldn't have worked. And you got to get all of them right. It doesn't count that you get 1, 2, and 3. You got to get 4 too. So how is this using shift registers? Basically, what you got, or excuse me, what you put in compared to what's in there. And then finally, it's also using this thing in basically a pass the 1 game. You got to get 4 of them right for you to get the 1. Okay, so let us conclude shift register applications and move on to memory.